Okay, I'm going to start with some applications. So some of these slides are a sort of repetition of what you saw earlier, but I will start with by motivating the type of problems that we are interested in. So typical image denoising model it goes back to the work of Rudin, Osher, and Fatami, where if F is a noisy image and you want to reconstruct U, um, so that's what the second term in the first functional points to. And then the first term is you're trying to regularize U with the help of the so-called total variation regularization. This is a challenging problem because if you, at least formally speaking, if you write the Euler-Lagrange equations, they are nonlinear and degenerate. And still people are writing papers on this model, even though it was introduced a long time ago. And still it's highly relevant, especially for imaging applications and also applications arising in phase field models. A few years ago, together with my friend Soren Bartels, we replaced this total variation regularization by the so-called fractional Laplacian regularizer. And then, then the advantage of this problem is that the Euler-Lagrange equation now are just a linear equation actually. So, but you may say that it's still challenging to solve because you have fractional Laplacian sitting over there. I claim that since the images are given typically on rectangular or square tap domains, so you can just take fast Fourier transform in MATLAB. It's extremely cheap actually to solve this problem. So here is a picture where if you start with a noisy image like F given here, which is the second image on my slide, and if you solve this problem for exponent s equals 0.4, I think, and this is the recovery you get, which is the third image. And the right image is what you get if you use the total variation model, where you even optimize over this regularization parameter alpha. So we notice that this fractional model actually can capture jumps as does this total variation based model. Of course, we still need to identify this fractional exponent s and this parameter alpha, especially with respect to this fractional exponent s. The problem is non-smooth, non-convex, but we have actually now a neural network based model or a bi-level optimization based model to identify this fractional exponent s, but I won't go into details of that. I can point you to a paper on that subject. And then we were a bit more adventurous with my friend and colleague Carlos Rothenberg, where we were curious, see if we can make this exponent s a function. We don't take it a constant any longer, but we make it dependent on the spatial variable x. And we also wanted to touch the extreme values 0 and 1, especially when you have jumps. You want to set this s to be as close to 0 as possible, right? So then you are just an L2 function. You are not doing any smoothing. And that's what you see in the numerics as well. So if you start with a noisy image on the left, this middle image is what you get if you do recovery using total variation regularization. TV has this artifact where it tends to round up the corners, and the right image is what you get if you do um, recovery using this fractional Laplacian with variable exponent as the regularizer. So and there are some other works we have done in this direction, where you're given sort of a cloud of data and you are trying to fit a manifold through the data. This is called manifold learning. This technique is used quite a bit in machine learning, where we are trying to reduce the dimensionality of the data, and typically they use standard heat kernel, and the resulting operator is the so-called Laplace Beltrami operator. But here we propose that why not use these non-local kernels, which leads to actually fractional Laplacian. And we noticed several interesting features. And this is a paper which is about to be accepted in applied and computational harmonic analysis. So these were the applications from the data science point of view, where we see it makes sense to use fractional Laplacian as a regularizer because it can capture jump discontinuities. The another application from a physics point of view that Professor Jose Francisco mentioned is the so-called magnetolurics. So the goal here is you're trying to infer the electrical conductivity inside the Earth. And typically, to model this phenomena, people use so-called Helmholtz type equations. Few years ago, already when I was visiting Lisbon, actually, we were finishing this work at that time. So we derive the so-called fractional Helmholtz equation starting from 3D Maxwell's equations using first principle arguments combined with a constitutive relationship. And that's one thing we do, and this work is published in this Geophysics Journal International. Recently, we have done a full analysis and numerical analysis of that model, which is published in the Siam Journal of Scientific Computing. We notice in the first paper that once you do numerical simulations using fractional Helmholtz equation for something called apparent resistivity with respect to the frequency, you see this inward bell-shaped curves. With here 0.5 denotes the fractional exponent, 0.6 is also the fractional exponent. And then we were wondering if this data, this computational data actually does corresponds to anything physical or not. And so, while we were developing these models, so my collaborators, they were organizing a mini symposium at a big geophysics meeting with 25,000 people. And we showed our numerical simulations to some of the people who were attending this meeting, and they pointed us to this data from a magnetolurics station located in the state of Kansas, where notice that the behavior or qualitative behavior of this real data in our solution is almost exact. So this really motivated us to study fraction PDEs further. Recently, actually pretty much like yesterday and last week, we have developed new models for director field and surface PDEs when it comes to the classical models. So in the classical, for example, like liquid crystal type models, you see the so-called point defects and the line and line defects. And this is an important technology. But with fractional models, we can also get so-called non-local defects. And I hope I can show you that paper in a couple of weeks. It's almost ready. That's another application coming from physics, which I'm not getting into too much detail right now. So here is a quick outline of the talk. I hope everybody is motivated now to hear further what I have to say. So I'll start with the definition of fractional Laplacian and some function spaces. I'll briefly mention some implementation aspects. Then I will mention some of our work on optimal control of fraction PDEs, and then something which will be of interest to your group is we have developed a fractional version of the classical Murat result with respect to the convergence of non-negative distributions, and we apply this to show the existence of solution to some fractional quasi-variation inequalities. If there is time, I will mention some of our recent work, which we submitted actually just 2 days ago on deep neural networks. But if there is no time, then I will skip that last topic. So let's start with the very basic definitions of fractional Laplacian. There are various ways of defining this fractional Laplacian. especially in bounded domains. In unbounded domains, everything coincides. The first definition is you take the eigenfunctions and eigenvalues of standard Laplacian with zero Dirichlet boundary conditions, and then you raise just the eigenvalues to the power s. That's how you define the so-called Dirichlet fractional Laplacian. But notice that you are building inside this object zero boundary conditions. We've extended this together with the former postdoc, this object to incorporate non-zero boundary condition. That required changing this definition slightly. And you can find that in this paper, which is published in Communication in Mathematical Sciences. Then the other definition is the so-called integral fractional Laplacian, where you define this object in the principal value sense. And here CNS is just a normalizing constant. And notice that this is a non-local object, because if you're trying to evaluate this object applied to X, you need to integrate over the entire Rn, right? So you need information everywhere. If I replace this Rn by omega, you get the so-called regional fractional Laplacian. Now let me point out that these operators are different, and the corresponding PDEs are different than the classical PDEs. Let's look at this integral fractional Laplacian case. The classical Poissonic or the Laplace equation is minus delta u equals to 0 in omega, and you enforce some Dirichlet boundary condition u equals to g. Now, if you try to do the same with the integral fractional Laplacian, you notice that that problem is not well posed, and that's due to the fact that you need information about functions everywhere, right, in the exterior. The well posed problem is you enforce the conditions in the exterior of the domain. All right. Now we have the sense on how to define the problem. We also need to understand the integration by parts formula when it comes to fractional operators. So I will start by introducing the so-called interaction operator, or the so-called non-local Neumann derivative. So this is again a non-local operator, but here the kernel is not singular, because X is in the exterior and you are integrating on the omega. So this is allowing you interaction between outside and inside. And as S approaches 1 from the left, you can show that this non-local operator in fact does converge to your standard normal derivative. So now we have the notion of normal derivative, so we can define the integration by parts formula. It's analogous to the classical integration by parts formula, where grad is minus v Laplacian u plus the v times the normal derivative of u. We replace this term by again another bilinear form, but we have the non-local object here, and delta u you replace by fractional Laplacian, and this normal derivative you replace by this non-local Neumann derivative, or this interaction operator. Now, we saw at the beginning of the talk that there are applications where we see that that the fractional Laplacian regularizer can capture sharp transitions, and there is something which really distinguish this is something that really distinguishes you from the classical problems. One example is, just consider the standard Dirichlet problem as written here in the first bullet, and let's take a smooth domain. Omega is a unit ball, f is 1, and the right and the boundary or the data in the exterior is 0. So if you have such a data and such a domain, for the classical Poisson problem, you will get a smooth solution. But this is not the case when it comes to fractional Laplacian. You actually get a non-smooth solution. In fact, the shift theorem does not hold for this example. All right, so this was sort of a quick background in case you are not very familiar with fraction PDEs. And we also need to introduce some Sobolev spaces. So here I'm defining WSP space functions in LP so that this Gagliardo semi-norm is finite. Correspondingly, we define norm on the space. This is the standard thing. If you take P equals to 2, you get Hilbert space. I will also make use of the space WS20, which is the functions in WS2 Rn, which are 0 in the exterior of the domain. I want to emphasize that this is these spaces are defined in the sense of Basov spaces. I'm going to introduce later when I talk about some fuzzy variation inequalities, the so-called spaces coming from Bessel potential, and they are not necessarily the same in general. For the fractional Laplacian with spectral for the spectral fractional Laplacian or the Dirichlet fractional Laplacian, I will make use of this space bold HS, which is defined as an interpolation space between H10 and L2. And you can also define the norm using the eigenvalues of the Laplacian. Okay, so there was a lot of heavy notation, but just want to recall again that so far what we have established is we have several applications coming from data science, coming from physics. One application I mentioned related to defects that I didn't get into too much detail, and then we introduce some of the notation. Now I want to quickly mention some of the references that deals with various aspects of implementation when it comes to fractional PDEs. So this slide is just to let you know that there are many works in this direction, and I won't get into any of the details. When you have periodic boundary conditions, you can use Fourier transform to solve the problem. There is a work by Ainsworth and Mao, and also the work that I mentioned at the beginning together with Søren Bartels. Then there is the spectral fractional Laplacian. You can use the so-called extension approach or so-called Caffarelli-Silvestri extension approach to solve PDEs that corresponds to the spectral fractional Laplacian. And you can also use an alternative approach from function analysis that's using the so-called Kato formula. This is a pretty neat approach, actually. Unfortunately, I don't have time to get into detail, but if you're interested, you can download the code for this approach from my website, or I'll be happy to follow up with you. Then the other approach is the spectral approach, where if you can afford to compute the eigenvalues and eigenfunctions of Laplacian, then you can also approximate the operator. We know that in general, this is a difficult approach. For the integral fraction Laplacian, things are much more complicated because you have to resolve the singular kernel, especially in more than 1D. This is highly challenging. The first work in this direction, as you can see, these are very, very recent works, is by Gabriel Acosta and his former PhD student Juan Pablo Bordagaray. This works in 2 dimensions. Then the other work is by Andrea Bonito and collaborators. They use this Kato representation that I mentioned above. There's a recent work that we just submitted a couple of months ago together with the group in Freiburg, Germany, where we use a spectral approach to approximate the integral fraction Laplacian. And surprisingly, it works extremely well in both 2 and 3 dimensions. Actually, it's not really surprised, but once you go through the calculations, and it has a linear complexity, which is quite important if you want to create a good solver for these non-local objects. Sorry, I went too fast. Okay, now let me say a few words about optimal control of fraction PDEs. So what's the current state of the art in this direction? So, there are various ways of defining control. So you can put the control variable Z, for example, in the interior or the so-called distributed control problem, or the control could be on the boundary, right? So basically control problem is you're trying to minimize some objective function J subject to some PDE constraint. And you can have constraints on the control variable Z or on the state variable U. So, and you can work with the spectral fraction Laplacian or the integral fraction Laplacian. And here I'm writing a semi-linear problem as PD constraint. In these two works, together with a couple of my collaborators, we developed a Sobolev-Orlik framework to identify a minimal regularity that you need on Z for the problem to be well posed. Then we show that the solution is bounded using this Stampacchia cutoff function argument. And we also developed the finite element error analysis for these PDEs. For the control problem, typically, if you want to show the existence of solution to the problem, you assume that F is locally Lipschitz, which leads to that the solution map is Lipschitz. We replace this Lipschitz requirement on F by a growth condition, which is not a regularity condition, and it seems somewhat general. We also derive the second order sufficient optimality conditions for this control problem, and so that's where we stand at the moment. We have extended, so we are actually currently extending this this framework to semi-linear problems, where we consider fraction derivative in time. So semi-linear parabolic problems where we consider the fraction derivative in time as well. And we have an extremely general framework that can deal with a large class of problems. This paper will be hopefully coming out in a month or so. Okay. So for the spectral fraction Laplacian, you can actually have the control just on the boundary itself. That's not a problem. But for the integral fraction Laplacian, the control needs to be in the exterior of the domain, which may seem artificial at first, but this allows us to introduce a new notion of control, the so-called exterior control, where if you're trying to control things in this square, you don't need to put the control in the domain or on the boundary, but you can have a control which is really far away from the boundary. So we have developed that for the elliptic as well as parabolic case, and these are the two references mentioned here. One thing you need to do is, so we only assume the control is in L2. So, but if you have L2 data, as we know even in the classical case, we don't have H1 solutions, we don't have weak solutions. So we need to develop the notion of very weak solutions, where you do the integration by parts twice. But this can be done. It's not that hard actually. But from the numerical point of view, this is much more challenging, because previously you started with one non-local operator, but now you have this non-local operator applied to the test function, and then this NS or the interaction operator or this non-local normal derivative sitting over there. So what we did was, instead of trying to approximate these two non-local operators, we approximate the Dirichlet problem by a Robin problem. And we can establish that, in fact, we have a rate of convergence with respect to this regularization parameter n. So as n goes to infinity, we do get a rate of convergence, not just convergence. Okay, so this worked out very well. Recently, we have developed, so we have extended this work to problems where we have constraints on the state variable u. Now the problem is much more delicate. So here I'm writing an operator A. It can be just the elliptic operator or the fraction Laplacian, or it can be parabolic operator, which is delta TU plus fraction Laplacian u. And we enforce the constraints on the state u is bounded. Let's say it needs to stay below a certain obstacle u sub b. We enforce also constraints on the control variable. So first thing we need to do is we need to establish that the solution to the PDE itself um, makes sense, and also this constraint makes sense in the sense of continuous functions. So for that we need this Z to be LP with P greater than N over 2S. It's analogous to classical case where S is 1. For the parabolic case, things are much more delicate, and we need so here the time and the space integrability mixes, and this is the optimal condition that's known in the literature for S equals to 1, but we introduce this condition for a general S. So the question is, why am I trying to impose this state constraints in the sense of continuous functions? Why not do it in this WS2 or in the Sobolev sense? The challenge is that in general, it's known actually in the classical case, the constraint qualifications may not hold in WS2 space, because this K tilde may, or our set of constraints may have an empty interior. So, and that's why we impose the constraints in the sense of continuous functions. But then, of course, there's no free lunch. That leads to another difficulty. The Lagrange multiplier are measures. So just coming back to the PDE itself again, if you take Z to be LP or Z is LR LP, we can show that the solution is in L infinity. But we need, so, and this holds for omega, which is a Lipschitz continuous domain. But we need solution to be continuous for both the parabolic as well as elliptic problems. Here we need to assume slightly more smoothness on omega. We need this exterior ball condition to show that the solution is continuous up to the boundary. And we needed this condition because our argument for continuous solutions is based on a paper of Rosothorn, and they work with this condition. For the control problem existence, we also need to assume the so-called Slater's condition. That is, you have at least one interior point. Right. Okay, so we can write the optimality conditions. We have a state equation as written at the top. Then we have the adjoint equation. In the elliptic case, we get this adjoint equation with a measure on the right-hand side. In the parabolic case, we also get a measure at the final time. So we have measures in both time and space. And for the control, we get this so-called variation inequality. And for the measure, we have this complementarity condition. Now, if you want to study, so this adjoint equation is the key challenge here at this point. So we are working with fraction PDEs, so is measure on the right-hand side. We can establish LP solutions for this problem, as mentioned here. The C bar is an LP prime in the elliptic case, and LR prime and LP prime in the parabolic case. But if you want to do some numerics later on, we want to establish a Sobolev regularity. And that's a challenge actually. And that lead to a very interesting project. So as I mentioned, the difficulty is that your adjoint equation has a measure on the right-hand side. How do you deal with this situation in the classical case? In the classical case, what you do is, if you have a function which is an h minus 1, we know that you can write this as sum of an L2 function plus divergence of an L2 vector in the weak sense. That's written here. This characterization is very well known. Surprisingly, this characterization was not known for this W minus SP primes Sobolev space. And we established that in a paper which is now published in Journal of Optimization Theory and Applications, just got accepted at the end of last year. And then if you have this characterization for fraction order Sobolev spaces, then you can actually show that you don't need data or you can show that the solution to this PDE is not just in LP, but it belongs to a certain Sobolev space, this WT prime. We've gone, so this was about optimal control problems, fractional optimal control problems with state constraints. We have shown the continuity of solutions. We have established this new tool in analysis, the characterization of the negative order, fractional order Sobolev spaces. With the help of that result, we are able to establish the high regularity for the adjoint equation, which is the fraction PDE with the measure on the right hand side. How do you solve this problem? One way is you relax the state constraint by using the so-called Moro-Yoshida type approach, where you regularize with the help of L2 norm of a max function. And now things are much better because this is an L2 function. You can establish a weak solution to the adjoint equation. We have done some analysis also in this, where if gamma was the regularization parameter, we study the rate of convergence with respect to gamma. The results are analogous to the classical case, but we needed some new tools to get these results. So let me keep track of time. 38. So all the problems that I discussed so far, the control problems, I took S to be a fixed constant, right? But how do you identify this exponent S in practice, and especially for optimal control problems? That's not so obvious. So what we did in a paper, which is just got accepted actually a couple of weeks ago in Scientific Journal of Control and Optimization, we make this fractional exponent S to be a random variable. If we do that, then the solution U to the PDE becomes a random field, and your objective function J becomes a random variable itself. So then what does it mean to minimize a random variable, right? One thing you could do is you take the expected value and you can try to minimize that. In the classical stochastic programming literature, this is known as the so-called risk neutral case. They have more sophisticated risk measures. One example is you are minimizing the sum of expected value plus deviations just above the expected value. The other example is the so-called entropic risk, which looks a little easier to deal with in numerics especially. But in this paper, we have developed, so these are just some examples of risk measures, but you can develop a whole theory around, you can develop a general framework to deal with large class of risk measures. And we did that in this paper. And the key difficulty was, since our exponent S was a random variable, so, and the solution space is HS. So then that means the solution space is random as well. So what does that mean? So to answer that question took some effort actually. And that's what we are doing in this paper. I'll be happy to discuss this further if you're interested. All right, so this was the section on control. I know it was maybe a bit of mouthful, but I'm happy to discuss and follow up with you guys. But let me quickly show a new result that that we worked out last year. So Armin Shikora, he's a professor at University of Pittsburgh. He was visiting me last year, and then we started talking together with Rautenberg. We were interested in this classical result of Mura, which was proved again by Bretzies, and I'm going to talk about that result on the next slide. But let me introduce some notation first. So here I'm introducing the fraction order Sobolev spaces using the so-called Bessel potential. Fractional Laplacian is the same as before. but now I'm defining the fractional order Sobolev space, this HSP00, as functions which are in LP, and this fractional Laplacian SO2 is in LP, and F is 0 in the exterior. So the setup is pretty much the same, only this condition is different. Instead of using this Gagliardo semi-norm that I was using before, this is a slightly different condition. And we define a norm on the space as LP norm plus delta S over 2F and in LP. You can show that the smooth functions with compact support are dense in this space. And you can also establish a Poincare inequality so that the second term forms a norm on this space. This is a paper with my colleague and friend Carlos Rautenberg and Armin Shikora from University of Pittsburgh, currently in review with SIAM math analysis. So the key result was this one. So let's say omega is an open bounded set. We do not assume any more regularity on omega. This is what Bretzies also did. But they were focused on the classical case. And let's say Hn and H are in this dual space, this HS2 omega star. S is between 0 and 1, including 1. So it's we are in a general setting. And this Hn are non-negative in the sense of distributions. And Hn converges to H. So you have convergence of this sequence of distributions which are non-negative to H in this the HS2 space, in the dual of this HS2 space. So then we can establish that in fact you get a strong convergence of Hn to H in this dual space. So you go from weak convergence to strong convergence provided this Q is less than 2. So this result for H012, which is the classical Sobolev space, I don't know why I wrote it this way, but it's okay. So is due to Murat, right? So in the classical case, we just write H01. We don't put 2, but this is just an analogous to this. And this was proved again by Bretzies. I think he shortened the proof significantly, and I'm not joking. So the proof of Bretzies is like half a page compared to Murat's long paper. So we have generalized these results significantly to the fractional order Sobolev spaces. In fact, we have generalized even the classical result because our proof also worked for H01P spaces. So we don't need to take S here in general, but it works for H01P. So they only work with P equals to 2, and our result works for any P greater than Q. So we have provided like a significant extension of their result. And the main premise is the same, that if you have non-negative distributions, it can be treated as measures. But the proof is significantly longer. Maybe Bretzies has an easier way to prove this as well. Okay, so what do you do with this result? One thing is you can talk about convergence of closed convex sets. If omega is an open bounded set, and let's say this obstacle psi n converges weakly to some psi in the HSQ space for Q greater than 2, then you can establish the convergence of the Ks psi n as written here to in the sense of Moscow to Ks psi. This is a result for the case S equals to 1. It goes back to 1982 by the work of Boccardo and Murat. And this result is critical to study the stability of variation inequalities and several optimization problems. In fact, we did apply this to a quasi-variation inequality case, where if F is in a certain dual space, and you're trying to identify U in the set Ks, where this map phi depends on the solution U. So this is more general than your standard variation inequality. Then you can establish using the previous result that I mentioned, that this problem has a solution. All right, so this was the work on quasi-variation inequalities. We have several other results actually related um, to fraction PDEs. For instance, we have developed a multi-grid framework for optimal control problems, which is quite an efficient method to solve optimal control problems with fraction PDEs as constraints. We have looked at fractional PDEs where you not only have where the operator is not the standard fractional Laplacian, but it's a fractional P Laplacian. And the goal of this optimization problem was to identify the coefficient in that fractional P Laplacian. And we regularize this coefficient. We use the total variation regularization. We have some. I already mentioned this work on fraction QVI. We also have a result on fraction QVIs where the fractional Laplacian was the spectral fractional Laplacian. And in this new paper, we also, I mentioned this result of Mura and Bretzi, and also Bocardo and Mura, but we also developed we also stated several new compactness results for fractional order Sobolev spaces in this paper. We have developed some reduced basis type method to solve fraction PDEs. And these are published in these two papers in SIAM Journal of Scientific Computing and Math Control and Related Field. And then, I talked today, I mostly focused on optimal control problems, right? But there is the notion of controllability, which is slightly different community. And we have a work which is currently in review. In this math paper, takes a long time to get published, but I won't get into too much detail. Just want to say that these controllability problems, if you're trying to impose constraints on the control and the state for this controllability problem, it's very, very delicate. And we have a work which is in one dimension, but it's pretty nice actually. So I don't know how much time do I have.
10 minutes, at least 10 minutes.
10 minutes. Okay. So then I can introduce one more object. So far what I have discussed is started with some applications, discuss some optimal control of fraction PDEs, discuss this new result, which extends this classical result of Mura and Bretzi significantly, and applied it to quasi-variation inequalities. But at the beginning of the talk, I also mentioned this object delta SX, right? So the first slide that I showed you guys, we had a problem where we were trying to denoise this noisy image F, and then I said that let's use this fractional Laplacian as a regularizer. And then I showed you an example on the second slide where I replaced this with this delta S of X. Right, X was spatially dependent, and we allow X to touch 0 and 1. Especially this is important if you don't want to smooth out the discontinuities. Now, the main road, when we start thinking about this, the main roadblock was how do you even define such an object? So there was one thing that I didn't mention. I mentioned rather quickly is if you have, I don't know if you can see the board, but there is this notion of Caffarelli-Sylvester extension or the Stingatoria extension. If you are trying to solve a PDE in this domain omega, and if you look at, if you're trying to solve minus delta S U equals to F in omega, but instead you can solve a PDE of this form, divergence of Y alpha gradient capital U equals to 0 in the cylinder, and you have certain boundary condition on the on the side of this cylinder, and then you impose certain normal condition at the bottom.
Arbir, I think you should stop sharing screen
Right.
if you show the
Yeah.
black.
Good point. Sorry, thank you. So if you're trying to solve this PDE in omega, this fraction PDE in omega, another one, especially with the spectral fraction Laplacian, one way to solve this is you look at a problem in this cylinder C, which is omega cross 0 infinity. And in this cylinder, you look at the following local problem. Even though this is a semi-infinite object, local problem is divergence y alpha. Y is the variable in this direction. This is x. Alpha is 1 minus 2s. So, and if you solve this problem and you take the trace of this capital U in omega, you recover the solution to the original problem. So that's the only thing I wanted to mention. So let me go back to my slides. So can you see the slides?
Yep.
Okay, excellent. So what we did was, instead of trying to define this object directly, we look at the extension problem, and we make S as a function of X in the extension problem. And that's what's written here. We write it as a variational problem. If S is a constant, strictly between 0 and 1, then this reduces. So then this problem and this problem are completely equivalent. Okay. But now we have a more general framework where we can develop equivalence between these problems as well. But I won't discuss that today. Let me quickly mention what are the difficulties that comes when you try to understand this variational problem. First thing we need to do is we need to introduce the Sobolev space on this semi-infinite cylinder. And now you have a weight which is variable. It's not just depending on the variable y in this direction, but it also depends on this x variable. From harmonic analysis point of view, if S was a constant and strictly between 0 and 1, you can establish that the weight is of the so-called Mukhinov type. But in our case, we are making this S as a function of X, and we want to make sure that this S is allowed to touch 0, as written here in this third bullet. We can establish that the weight that we are working with, this weight in this Sobolev space, this is not a weight of Mukhinov class. And as a result, it's not so clear if the smooth functions are dense or not in this space. We establish a new trace result. So in the standard case where delta is not a function of x, the trace space is just standard L2. But we notice that the trace space is it's a weighted L2 space. And we have further characterization of this trace. We are getting close to the range of this operator, and this is part of a forthcoming work. Okay, let me say a couple of words on implementation and what type of results do we get. So here I start with such a noisy image. The noise level was rather high, and this is the recovery. The bottom left is what you get if you use the total variation regularization, and this is the recovery that you get if you use this fractional Laplacian as a regularizer. And in terms of this so-called SSIM, or the structural similarity index, I mean, we are close for this example. So we are doing slightly better. But for this, the classical cameraman problem, we do significantly better, in my opinion. So here it's like 0.79, and this is 0.74. So I don't think I have too much time left. So I won't take, I probably will skip this last section. And so just want to quickly say that if you want to solve parameterized PDEs like this, where u is a function of parametric c. For example, for the problems that I'm discussing today, c could be your fraction exponent, or it could be some unknown boundary data. So how do you solve these type of problems efficiently? People use the so-called reduced basis method, and that's a couple of works that I mentioned earlier as well. But we have developed a framework based on deep neural networks to solve this problem very, very efficiently. And I won't get into any details. We have some analytical result as well in this direction, but I just want to show you the savings in terms of time. So in this example, we're working with a nonlinear PDE, and we're trying to identify this fractional exponent, not fractional exponent, this parameter c, and it's a two-dimensional parameter. And we use this, we're trying to identify this within this Bayesian inversion framework. So the time reduction using this neural network approach, or our neural network approach. So we were taking this 2 minutes over a full model, which was like 40 minutes. And this is significant when you increase the dimensionality of the parameter space. Anyways, just want to recap that I started with several applications related to imaging, magnetolorics, fraction diffusion maps. I discussed a nonlinear fraction PDEs and optimum control, where the control could be a distributed control, or it could be a control on the boundary or in the exterior. I briefly mentioned this work on risk averse control, where we make fraction exponent as a random variable. I also mentioned some of the work related to causal variation inequalities. And then I also discussed this object, the delta S of X. And thank you very much for your attention. Jose Francisco, you're muted, I think.
Yeah, thank you very much.
Thank you very much for your very stimulating and exciting talk. Plenty of exciting problems and new results. And in fact, I forgot to tell at the beginning now that you are the director of this new Center for Mathematics and Artificial Intelligence at GMU. And this is connection exactly of this, maybe last part of your talk that you just dropped to these neural networks, connections with artificial intelligence. But this is maybe for next time.
Exactly.
For this time, we have time for questions. And of course, please make yourself unmute and ask, or just